Hello, and today we'll be talking about bacterial transformation. Now, when you're watching this, you probably have an idea of what this entire lesson will be about, or you at the very least understand certain words or definitions within this lesson. Now, either way, even if you do know, then I will still go over two or three simple words that are very commonly used in bacterial transformation. Now, bacterial transformation is the bacteria's ability, you should probably put ability there, to take up foreign DNA, or the process in which bacteria takes up foreign DNA. Competence is a very important word to use in this because competence is the ability of a bacteria to absorb foreign DNA, and bacterial transformation is all about taking up foreign DNA. A competent bacteria is a bacteria that can take up foreign DNA because its cell wall is more permeable, or, well, more likely to take up any outside DNA or plasmids. Now, moving on, there are two types of bacterial transformation: natural and artificial. We'll be going over these two soon enough, but we'll be going over artificial after we go after natural, because natural out of these two is the most simplest one. Now, natural bacterial transformation is when a bacteria is naturally competent. There are 40 recorded bacteria as of now that are known to be competent, but in the off chance that a bacteria isn't competent, then it'll either take up foreign DNA through perhaps a sudden shock or heat that causes the cell wall to become more permeable for the foreign DNA, or it'll go through artificial bacterial transformation, in which it shall go through the process of heat shock or electrophoresis. Now, in the first step of the first process of natural bacterial transformation, we have the chromosomal DNA. The chromosomal DNA has the original DNA of the cell, which is why this would be the recipient. This one cell would be the recipient to take up any foreign DNA. Now, the bacteria can take foreign DNA from several places, like a plant or maybe somewhere on the ground. Bacteria is everywhere, and DNA as well has a chance of spreading throughout surfaces. So now we have all this DNA, outside, or DNA fragments, and they can go inside here, but they won't. Well, this is already a competent cell, because if it weren't a competent cell, then this process would most likely be artificial, not natural. Now, when the next process or step would be when the DNA actually gets in the cell. The when this happens, now we all know what competent means. It means that it's more like that a bacteria is willing to take up foreign DNA. I've already repeated that several times throughout this one single video, so I'd like to think that you're all aware of that fact. And when when I say that it's competent, then that means this all that DNA outside of it from a donor cell or maybe a the gene of interest, it would be more likely to get inside. Then when it goes to the very last phase, the 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 faulting DNA would end up finally mixing or maybe even joining with the original DNA. Now this faulting DNA could be a lot of things. It could be something that makes the bacteria immune to antibiotics. It could be something that prevents it from going through asexual reproduction. What matters is that the DNA, the foreign DNA, mixes with the original. Now, I don't know if you're wondering this, but we can see that, well, the foreign DNA doesn't just go over the original DNA. The original DNA actually stays inside the cell as fragments that are going to stay there for a while or not going to be used. And if there's any left from the foreign DNA, it would also be a fragment. Now, when you can see here, the final would finally be a genetically transformed cell. We say it's genetically transformed because all of the foreign DNA has finally joined in with the original. And when we say recombination occurs between the donor DNA and recipient DNA, it means that the recipient DNA, this guy, and the donor DNA that's been from the outside, or you know, these little guys. Recombination would mean that these two would finally join to make one whole DNA with fragments from the old ones. And that's basically natural bacterial transformation. There's not much else to go in there, and even if there were, I would have a difficult time to articulate it to all of you because I am neither a expert at the subject. However, I will try my best to explain everything to you all. Moving on to artificial bacterial transformation, we have 4 steps with actual names. And this one's a bit more complicated than natural because unlike in natural, artificial bacterial transformation has certain things that should always be followed, like the temperature of say the heat used, or perhaps the temperature of where the bacteria should be stored. Now this would be something that some of you might have a difficult time at trying to understand. I myself had a difficult time trying to understand all of this. I've gone through a long time trying to understand this, and even now it's kind of hard for me to just, well, explain. So we'll just go here in competent cell propagation, which is step 1. Now, as you can see, well, this it's called competent cell propagation because you don't have a competent cell, or the bacteria or cell you have isn't competent. So what we do in this step is we we make the is we make this go through either heat shock or electroporation. Now the results are more or less the same with these two. However, it has been said that heat shock is more preferred because in electroporation, the cells themselves have a much more shorter lifespan than in compared to heat shock. The one thing that separates these two is that in electroporation you have to be more careful, I suppose, or a bit more careless. In heat shock, there are more what's the word? There are more elements involved, like some of the because in heat shock you have to incubate the cells in calcium chloride, which is this right here, and in and sometimes you have to add manganese, potassium, cobalt, or rubidium to improve its competency. Not always, but it you can add these things. Now you incubate the calcium chloride to make the cell membrane more permeable. Again, make the cell membrane more permeable. That's the main point of competent cell propagation, to have the so to have the to have the cell membrane more permeable for access, so that the plasmids have a way of getting in. Now you notice that in artificial by bacterial transformation, you see all these circle things, right? Not like in the natural bacterial transformation, where you would just have all the DNA outside and just the sickle thing itself. Now that sickle thing, that could be the plasmid itself, or maybe it could just be a nucleolus or nucleus. I can't say for sure, but here in artificial bacterial transformation, plasmids are an absolute must. They're developed just for this process. Well, not just for this process, but they're developed very frequently for this process itself. In now we have competent cell propagation, and we get the idea. It's to make sure that we use heat shock and electroporation to make to give the cell membranes a bit of heat or shock, so that they'd be more less strict, I guess, is a word you could use. Less strict on what kind of proteins or all sorts of stuff could go through and into the cell. Now we're in transformation. Don't don't mind that. That's just a typo. It's transformation, guys, not transformational. Make no mistake. Now, transformation is when the competent cells are thawed on ice to retain viability. When we say retain viability, it means it stays as a competent cell. We already have the competent cell now after the cell population. Now all we have to do is keep it that way. Again, electroporation and heat shock are used in this process. Believe me when I say that this is the last step where those two methods will be used. Transformation is more focused on, believe it or not, just having the plasmids get inside there. It's more focused on the plasmids getting a way in so that they could finally have their DNA, have the DNA, whatever foreign DNA they hold, and use it to make the bacteria adapt to a new evolutionized form, or well, that's basically it. Transformation is where all of the plasmids go and take their place inside. Then it's stored away or put on ice for a bit, just so it could keep its permeability and for the plasmids to stay. Now going to the recovery period. All of the cells are put in an antibiotic free liquid for a short period of time to let the antibiotic resistant genes acquired plasma to begin. Did that sentence make sense to you guys? I'm guessing it didn't. Well, the recovery period, the plasmid is now inside. The bacteria is most likely closed. I haven't really seen any comments on that about from the articles or videos. It doesn't seem like the the bacteria becomes less permeable to any other outside DNA, but I'm just assuming that it does close up or it does go back to how it was before the competent cell population, except with the plasmids inside it. During this recovery period, it's placed in a liquid medium so that the plasmids can actually acquaint itself with the genes or the original genes. And now moving on to plating. Plating is when, well, all whatever bacteria you used, it's placed on inside an agar plate. Agar plate, yes. That always has some antibiotic, because usually the usually the usually the plasmids placed into the bacteria so that it could begin to accumulate its abilities or whatever. Okay. The bacteria you tested, the bacteria you used, we can't usually immediately tell that it has the plasmid, but we will immediately tell if the plasmid has the we can immediately tell if the plasmids have this we can immediately tell if these bacteria have these plasmids whether they die or not, because the bacteria with the plasmids will survive because the plasmids are most likely things that that are resistant to antibiotics. So now you have everything. There's all of the bad, well, not bad, but all of the bacteria that wasn't needed are all dead. When that happens, the bacteria with the plasmids begin to form a cluster called a colony. Again, this one, I believe you've heard that word before. If not, then I'm afraid I can't delve into the topic, but a colony is a large group of bacteria who grow together or live in a similar space towards one another. There are big colonies, small colonies, but colonies all the same. Now when that's done, the colonies are checked whether they have the right plasmids, whether through PCR or restriction digestion. The colonies with the correct plasmids are placed into a bulk or grown in a bulk so it could be used for plasmids or protein production.